What's up, everyone? Today we're going to be talking about Fresnel diffraction. So now we're looking at the same diffraction experiment we discussed earlier in the Fraunhofer diffraction, except now we are within the near field zone. Because of this, we are unable to ignore the problematic issues with the Huygens-Fresnel principle as we did earlier. So let's define a spherical wave in better detail. Let's look at figure 1, right? That shows the 3 spheres and the concentric spheres coming off of it, and it's a secondary wavelet. It's on the left side of your screen. So at any instant, every point on the primary wavefront of a spherical wave can be envisioned as a continuous emitter of spherical secondary wavelets. The problem with this is that if we assume the wavelets are emitting spherically and uniformly in all directions, then some waves will, of course, emit backwards. And so we can see this in this diagram, right? Each of those points it blew up 3 of the points so that we can see what's happening, and that we can see the spheres radiating off the secondary wavelets radiate off of them. Okay. So the problem with this is that experimentally we do not see these waves backdraft occurring, is how we define this, of the waves emitting backwards, right? We're going to call that wave backdraft from this point forward. So since our equations are defined by physical phenomenon and not the other way around, we will have to fix our equations. To do this, we will introduce a new function, k theta, also known as the obliquity or inclination factor. And this, you can see, is on the right side of the screen, is a diagram showing the k theta. So Fresnel knew that he would have to introduce a quantity such as this, but never did anything but think about it theoretically. Instead, Kirchhoff picked off where he left off and gave us the k theta expression, where k theta is equal to 1/2 of parentheses 1 plus cosine theta, where theta is the angle made with normal to the primary wavefront vector k, as shown in the first image. This equation has its maximum value at 0 and fixes the non-existent backdraft problem, because when theta is equal to pi, then the equation would yield the proper 0 value. And so as you can see on this image, the wave is only emitting forward, right? There's nothing coming back. When it comes to the back, it's 0, which is what we want to see, because that's what happens in nature. And we want to make sure our equations are actually telling us what happens in nature. So the only other problem with the Huygens-Fresnel principle was to add up all of the secondary wavelets and reconstruct a primary wave, which we can't do. The propagation of a spherical wavefront can be described as any of the harmonic spherical equations, such as this, where E is equal to that equation, right? That's our most basic form of a harmonic. So we can take this wavefront and divide the wavefront into a number of annular regions, and the boundaries of these regions would correspond to the intersections of the wavefront with a series of spheres centered at P, as shown in the image 10.51. This is one of the biggest concepts of this section. So each of these regions are described as the half period or Fresnel zones. Since each zone is finite in extent, we can actually define the ring-shaped differential area element as ds. So now we're looking at this diagram, this eyeball diagram, and we look at S. S is where the wave is being propagated from, right? And then P is where the observer is. And so the way we think about it is that if P was also emitting spherical waves, right, then where the 2 spherical waves intersected, you would be getting these annular regions, right? These little circular rings, depending on the radius of the sphere, of the observer sphere. And so that's what we're seeing in this diagram. Okay. Now, each of these point sources will radiate in phase with the primary wave from point S and act as a coherent source. Since the secondary wavelets travel a distance r to reach P at a time t, all will arrive with the same phase. The contributions of the optical disturbance at P from the sources on D is how we would is what the second image is showing. Now, the obliquity factor must vary slowly and can be assumed to be constant within a single Fresnel zone. So within a single one of these rings, change so slowly that we can actually assume it to be constant. From this, we can get ds as a function of r by doing some calculus, and the end result is the equation 10.75. Let me show you guys that. Right here, this is the equation for ds that we can get, assuming we're within one annular ring and K is acting as if it's constant. Now we can look at the equation 10.76. So this is what's going to help us define our obliquity factor when we plug it back into the Huygens-Fresnel principle. So the disturbance at P from the alpha zone can be described by the equation 10.76, where the amplitude E1 alternates from negative to positive. This alternation depends on the sign of L and means that the contributions from adjacent zones will be out of phase and therefore will cancel out. So that means that each of the ring, it will cancel out with the ring next to it. So the obliquity factor really matters because theta and L are proportional, but K is inversely proportional with them. And that means that E1 over K1 are independent of position variables. So then the zones of E1 and K1 are almost equal, but they increase slightly as L increases. And this corresponds to an increased number of emitters that we will see in the vibration curve later that I will talk about in a few minutes. However, since the distance to P also increases proportionally, the value E1 over K stays constant. And because of all of this, we are able to get to equation 10.87, which is the proper Huygens-Fresnel equation. So just to summarize the Fresnel diffraction, the primary wave propagates from source S to viewer P, and alternatively, we can say that the viewer at P has spherical waves propagating from it. The area where these waves overlap can be approximated with the differential area ds, as in figures 10.51 and 2, the ones that look like eyeballs. The primary wave propagating from point S can be written in the equation 10.86, which is the original Huygens-Fresnel principle. But to account for the secondary wavelets, we need to use equation 10.87, which takes into account the obliquity factor. And so that means that 10.87 is the corrected version that accurately portrays what happens in nature. So with these changes, we can accurately describe what happens in our experiment while only slightly altering the Huygens-Fresnel theory. So next, we're going to be talking about the vibration curve. So here is an image of the basic vibration curve that all the other ones are expanded upon. Cameron will expand on this idea in his video. So the reasons that the Fresnel zones are important is because each successive zone is 180 degrees out of phase with the adjacent zones, which means that they will destructively interfere with each other. So regions 1, 3, and 5 are in phase with each other and out of phase with regions 2, 4, and 6. The vibration curve is a way to visualize how these zones contribute to the disturbance at point P using phasors. So the goal of this session is to develop a graphical method for analyzing a number of diffraction problems that crop up because of the spherically symmetric setup. And these are, of course, the same problems that I discussed earlier that are due to the original model not accounting for the secondary wave backdraft. So the first thing we do is divide each of the Fresnel zones into n subzones. To do this, we will imagine more spheres centered around P with radii that further divide each Fresnel zone into n zones. Zooming in and only looking at a single region between O and the circle with point Z1, these additional spheres will have radii of R naught plus 2 over n, R naught plus n, and then R naught plus 3 over 2n, and so on and so forth. And that you can see that in the secondary eyeball picture. It shows those. So each of the subzones bound by these circles contributes some amount to point P, but we will discuss this more in the next section. The contribution of each subzone to the disturbance at P can be represented as a phasor vector. Figure 10.51 depicts the phasors addition of the subzones in region 1 when n is equal to 10. So in this picture, E1 is the contribution at point P of region 1. And one thing to note is that we see here is that the sum of the phasors deviates from the circle because each successive subzone has a slightly smaller amplitude because of the obliquity factor discussed in the last section. With this fact, and with increasing the number of subdivisions into infinity, we can create a smooth spiral known as the vibration curve. The vibration curve allows us to see exactly why the obliquity factor is so important. The circle represents the original Huygens-Fresnel equation, ignoring time, because it's a wave function, which means that ignoring time, it would just be a circle. The obliquity factor accounts for the secondary wave backdraft, so each phasor shifts slightly off of the perfect circle, spiraling inward to create the vibration curve that we see experimentally, and Cameron will expand on this idea in his video. Thank you for your time.